Welcome back. In this module, we talk about encryption fundamentals and how data is protected at rest and in transit. Encryption is one of the most frequently mentioned concepts in cybersecurity and one of the most widely misunderstood. It is often spoken about as if it were a protective spell. Once data is encrypted, it is assumed to be safe. This belief is comforting. It is also incomplete. Encryption is a powerful tool, but it is not a guarantee of security. It protects data only under specific conditions against specific threats and only when it is implemented and governed correctly. To reason clearly about cyber risk, you need to understand what encryption actually does, what it does not do, and why so many real world failures occur despite encryption being in place. What encryption really is. At its core, encryption is a method of transforming information so that it cannot be understood by unauthorized parties. Readable data, often called plain text, is converted into an unreadable form, ciphertext. Only someone with a correct cryptographic key can reverse that transformation and restore the original information. Encryption exists to protect confidentiality. In some contexts, it also supports integrity by making unauthorized modification detectable. What encryption does not do is decide who should have access, when access should occur, or how data should be used. Those decisions are made elsewhere. Encryption protects data, it does not manage trust. Why encryption exists at all? Encryption exists because digital systems are inherently copyable. Data can be duplicated instantly, transmitted across networks, stored in multiple locations, and accessed remotely. Without encryption, any system that touches data becomes a potential point of exposure. Encryption introduces friction. If data is intercepted, stolen, or accessed improperly, encryption ensures that the content remains unreadable, provided the key is protected. That condition is critical. Keys are the real asset. In encryption, keys matter more than algorithms. Modern encryption algorithms are generally strong and well studied. Most real world encryption failures do not occur because the mathematics is broken. They occur because keys are mishandled. Keys may be stored insecurely, shared too broadly, reused improperly, embedded in code, or exposed through logs or backups. From a cybersecurity perspective, many incidents attributed to encryption failure are actually failures of key management. Understanding the shifts focus from abstract cryptography to practical governance. Symmetric encryption or shared secrets. Symmetric encryption uses the same key to encrypt and decrypt data. This approach is efficient and fast, which makes it well suited for encrypting large volumes of data. It is commonly used to protect files on disks, databases, and backups. The challenges with symmetric encryption is trust. Anyone who possesses the key can read the data. Protecting the key becomes as important as protecting the data itself. If the key is exposed, encryption offers no protection. Symmetric encryption is powerful, but only when key access is tightly controlled. Asymmetric encryption, solving the trust problem. Asymmetric encryption addresses the key sharing challenge by using two keys, a public key and a private key. The public key can be shared freely. Data encrypted with it can only be decrypted using the corresponding private key, which must be kept secret. This model enables secure communication between parties who have never met or shared secrets before. It underpins many foundational internet security mechanisms, including secure websites and digital certificates. Asymmetric encryption is slower than symmetric encryption, but it solves a critical problem, which is how to establish trust at scale. In practice, modern systems often use both approaches together. Encryption in transit, protecting data as it moves. Data in transit refers to information moving across networks, between devices, servers, applications, and services. This movement is inherently risky. Data may pass through networks you do not control. It may be intercepted, monitored, or redirected. Without protection, anyone positioned along the path could read or modify it. Encryption in transit protects data while it is moving. Technologies such as TLS encrypt communication so that even if traffic is intercepted, its contents remain unreadable. This is what makes secure browsing, online banking, and encrypted APIs possible. However, encryption in transit only protects data between endpoints. It does not protect data once it reaches its destination. Encryption at rest, protecting stored data. Data at rest refers to information stored on disks, databases, devices, or backups. Encryption at rest protects data if storage systems are lost, stolen, or accessed without authorization. It is particularly important for mobile devices, cloud storage, backup media, or shared infrastructure. Encryption at rest does not prevent legitimate access. Systems must decrypt data to use it. This means that if an attacker gains authorized access through stolen credentials or compromised systems, encryption at rest may offer little protection. It is a safety net, not a shield. The gap between encryption and security. One of the most common misconceptions is that encrypted data is automatically secure. In reality, encryption is only one layer in a broader secure system. If access controls are weak, credentials are compromised, or keys are exposed, encryption becomes irrelevant. Data can be decrypted legitimately by the attacker. This is why breaches often involve encrypted data that was nonetheless readable by unauthorized parties. Encryption does not replace access control, it depends on it. Visibility and false assurance. Encryption can also reduce visibility. Security tools that monitor traffic may be unable to inspect encrypted content without special arrangements. This creates trade-offs between confidentiality and detection. Organizations must balance privacy, security, and monitoring carefully. Over-reliance on encryption without complementary controls can create blind spots. Security is about layers working together, not single mechanisms in isolation. Where encryption fails in practice. Encryption failures usually stem from poor key management, overly broad access permissions, insecure defaults, inconsistent implementation, and assumptions that encryption alone is sufficient. These failures are rarely technical in nature, they are organizational. Encryption is only as effective as the policies, processes, and people surrounding it. Why this matters for cyber risk. Encryption shapes how incidents unfold. It can limit damage when data is stolen, reduce regulatory impact, protect privacy, slow attackers, but it can also create complacency if misunderstood. Understanding encryption allows you to ask better questions. Where are keys stored? Who can access decrypted data? When is data encrypted and when is it not? These questions are far more important than algorithm names. The key takeaways are encryption is essential, but it is not magic. It protects data only when keys are protected, access is controlled, and governance is clear. Encryption reduces risk, it does not eliminate it. To use encryption effectively, you must understand its role within a larger security system and avoid treating it as a substitute for trust, oversight, or accountability.